Good evening. We're a little early, but I figure we'll start, and that way we give our speaker more time for some questions after. So welcome, everybody, to our third lecture in our spring series. I'm sorry I missed the last one. I heard some really great things about Rosalie, so that's great. I would like to remind you we have one more lecture in our series in 2 weeks from tonight, and the tickets go on sale tomorrow at 10 a.m. As you know, these we tending to sell out within 24 hours, so please, if you're interested in going, make sure you get your tickets. The next speaker is Alison Strom, who's one of our postdoctoral fellows. She's going to talk about distant galaxies, so it's really interesting stuff. I highly recommend it. I also want to remind you that we will have microphones out in the aisles there afterwards for questions. We ask that if you have a question, you go out and use the mic so that people watching online can hear it. Okay, the usual thank yous we have. The Norris Foundation, who helps fund this series. We want to thank them for their support. We want to thank our friends here at the Huntington for offering this beautiful space and their crew for really helping. And I want to also acknowledge all of our Carnegie volunteers who help with check-in. I think the process has gone very smoothly now. And so thank you to all those folks. Okay, well, I'm sure most of you know it's been a very exciting week in astronomy. I'm sure everybody saw the picture of the black hole, right? So I got many emails about the black hole. So that was very exciting. Those of you, if you've been away from your computer for the last few hours, you may have missed the 2 new Carnegie press releases that came out. So I thought I would spend a minute to tell you about them because they're very exciting results. The first is one from our astronomers out here in Pasadena, led by Joanna Teskey, Steve Scheckman, Jeff Crane, Paul Butler, among them. And this is the first release of the first discovery of an Earth-sized exoplanet from the NASA's TESS mission. So maybe you may know NASA launched a mission called TESS last year, which will find 14,000 exoplanets in the next 3 or 4 years. This is a very exciting mission. And so this is the first one that's being reported that's kind of Earth-like in size. But the interesting work that our team did here is, although TESS can find the radius of the planet or the diameter of the planet, it can't tell you the composition or the mass of the planet. And so to do that, you need to use ground-based telescopes, and our team used our telescopes at Las Campanas to measure the mass of that system. And so if you have the radius and the mass, you can determine what the object is made of, what its density is. And even though this object appears in radius to look similar to the Earth, it turns out it's actually more like one of the the outer planets in the solar system, a gaseous giant. So it's really interesting work, but this is the first of many such exoplanet studies you're going to hear about in the next few years from TESS. So we're very excited about that. So you can read that on our website, or it's on CNN.com and various places. So we're very happy about that. Now the second press release happens to be by Larry Nittler. Now that name may sound familiar. And so the timing is really good, and I, of course, planned this a year ago. Larry is a staff scientist at our sister department in Washington, D.C., the Department of Terrestrial Magnetism. You can see they call themselves DTM for short. Now, this department doesn't do terrestrial magnetism, that is the magnetic field of the Earth. They stopped doing that almost 100 years ago. But the department does lots of interesting things, primarily a lot of planetary science. So a lot of their work actually overlaps very closely with what we do here in Pasadena at the observatories. And so Larry is a cosmochemist. What this means is he uses meteorites to try to understand the origins of the solar system, the origins of the Milky Way, how stars evolve. And that's the topic of his work tonight. The press release, I don't know, I think he's going to just talk a tiny little bit about it. Maybe we can get him to talk more during the question session, because it just came out today. The press release is very interesting because they found a meteorite that actually has a small, tiny little speck, remnant of material that appears to be from cometary material, which we think is quite in a meteorite, which is really interesting. So hopefully he'll say a little bit about that, and if not, we'll drag him up and have him talk about that after. Okay, anyhow, Larry gave a talk to our astronomers today up at the Carnegie observatories, and it was a really amazing talk. And so I know you're going to really love hearing about his work tonight. So with that, let's welcome Larry to the stage. Larry?
Thank you, John.
There you go. Enjoy.
Thanks. Yeah, I'd like to thank Dr. Mulcahy very much for the invitation to give this lecture. I'm deeply honored and privileged to be giving a lecture in this series in this beautiful auditorium on a gorgeous spring day in Pasadena. I also have to say it's a little hard to follow the sublime musical performance we just experienced, but I will try. What I want to do in the next hour or so is show you how my colleagues and I and researchers around the world use laboratory studies of microscopic bits of dirt that we find inside meteorites to learn about much grander, more spectacular, larger phenomena in the cosmos, like this supernova explosion. But I'm going to start with the elements. Some of you may know that the United Nations declared 2019 the International Year of the Periodic Table. And, and as we know, the periodic table rocks. It organizes in an absolutely beautiful way all the different elements we know of that make up everything. There are 92 naturally occurring elements on the Earth. There's another couple dozen of elements that we make in the laboratory. But of course, they don't all come in the same amounts. And for an astronomer studying the cosmos, what we know is that most of the universe is about the same composition as the sun. And it's 3/4 hydrogen, another quarter helium. Uh-oh. I think my microphone just fell off. No? It fell off my ear, but you can still hear? Okay. Then I won't worry about it. And everything else that we know of fits in this little 1 or 2% of the sun by mass. Of course, in our everyday life, we see far more elements than just hydrogen and helium, though hydrogen, of course, plays a huge role in our life because it's 2/3 of the atoms in a water molecule. But if we look at the abundances in the crust of the Earth, the rocks that we're standing on, it looks more like this: oxygen, silicon, and a bunch of other important elements. And still, the rest of the periodic table is still in this tiny thing. So there's a reason that there's more of one element and more than another. And I'm going to try and get into why this is the case and how we learn about this through meteorites and other things. So fundamentally, the question is, where do all these elements come from? And we now have a pretty good idea where all the elements come from, at least in principle, if not in all of the exact details. And we've known this for quite some time now, for example, that the hydrogen and helium was mostly made, with all of the hydrogen and most of the helium was made at the very beginning of the universe, very shortly, within minutes after the Big Bang, when everything was cooling very rapidly. The first things that happened was the formation of hydrogen and helium, and a little bit of lithium. And then we also know that the elements that are heavier than uranium are generally made in the laboratory, in particle accelerators or in nuclear explosions in a less nice way. But everything else in between is made in stars, pretty much. A little bit different for beryllium and boron, but everything else is inside stars. And this has been known, and many of you might already know this. But the question is why? Why do stars make elements? And this question is actually highly tied in with a different question, which is, why do stars shine? And the answer to this is mind-numbingly obvious. It's because they're hot. Things that are very hot glow and shine. So really, the question we should ask is, why are stars hot? And the answer is, when they start, they're hot because they're collapsing under their own weight and there's a lot of gravitational energy. But that doesn't keep them hot for very long. The reason stars are hot is because they have nuclear fusion happening inside their deep interiors. What is nuclear fusion? Nuclear fusion is when the nuclei of elements come together to form heavier elements. So right now, in the center of the sun, what's powering the sun, why the sun shines, is because there are hydrogen protons, hydrogen nuclei, being converted through a series of nuclear reactions into a helium nucleus. And a helium nucleus weighs just slightly less than 4 hydrogen atoms. And E equals mc squared. Energy is proportional to mass. So the difference in mass is released as energy in the form of a gamma ray that eventually, by the time it leaves the sun, it's mostly in photons. Much lower energy photons. This is the only rock song I know of, or pop song I know of, that's really about nuclear astrophysics. It's what I started my PhD thesis with, because I love the song if you're familiar with it. It really does sum it up perfectly. The sun is a massive incandescent gas. It's a nuclear furnace where hydrogen is being turned into helium at very high temperatures. As a little side thing, I want to mention that the energy released every time 4 hydrogen atoms go to helium releases about 27 million electron volts. Well, most people aren't very familiar with an electron volt. It's actually a very small unit. And so I tried to convert it into a more common, not more common, but maybe a more recognizable unit. It turns out each reaction is about equal to 1/millionth of a billionth of an M&M, the energy you get, the 3 kilocalories you get if you eat a single plain M&M. So I'm hoping this becomes a new standard unit of energy, because we can all relate to it. But the point is that that's not very much, except that the sun is a really big ball of incandescent gas. At the center, it's very high pressure. There's a lot of this happening. And it's happening so much that the actual energy being put out of the sun in these units is 3 times 10 to the power of 22 M&Ms being consumed per second. So nuclear fusion is a very, very powerful energy source if you can get it to work. And someday maybe we will be able to get it to work in laboratories and solve a lot of our problems. But at the moment, you need a very large ball of gas to get it to happen naturally. In about 5 billion years, the sun's going to run out of hydrogen in its core. It's going to just have turned all the hydrogen in the center to helium. At which point, it's going to start collapsing again under its own weight until it gets hotter and hotter. And when it reaches something like 100 million degrees, more fusion will happen. These helium atoms that were made, or helium nuclei that were made before, will start fusing into carbon and then combine with more helium to make oxygen. So the core will gradually become carbon and oxygen. Remember, we didn't start with carbon and oxygen, or we might have, but we're making more. This is nucleosynthesis. This is why stars make elements. Stars make carbon because hydrogen turns into helium, turns into carbon. It's alchemy. And it's really, what it means is nucleosynthesis is a side effect of stars making energy. We have elements, we exist because stars are trying not to collapse. Gravity is forcing them so close together that nature is conspiring to make the atoms come together and produce energy to push back against the gravity. So that's why we exist. The basic theory for this was largely worked out in the sort of 1930s to the 1950s by a bunch of people who are far smarter than me, and was really laid out the basic modern principles of how most of the elements are made in which processes, sometimes in which types of stars, sometimes not. It was worked out in the late 50s in a couple of seminal papers by Burbage, Fowler, and Hoyle, and independently by Al Cameron. And the broad framework was worked out, but not the details. And much of what they figured out was based on nuclear physics principles, where they could figure out if you had the right combination of temperature and pressure and composition, you could make this element. But they couldn't quite say what kind of star would do that. And we're still in this process of trying to understand where every reaction that makes the elements happen and how this is related into stars, how they evolve, how the galaxy evolves, and so on. This is a version of the periodic table that has become quite popular, at least on social media or science social media in the last couple of years. And I really like it quite a bit. It's where the elements are now color-coded by what type of star we think makes them, or Big Bang in this case. So you can see the hydrogen and helium is mostly made in the Big Bang, but most of the periodic table are in these different kinds of stars. And you can see that different elements are made in different types of stars by different processes. So you can see all the iridium here at element 77 is made in merging neutron stars, but about half the lead is made in dying low-mass stars and half in merging neutron stars, and so on. You can see most of the carbon and nitrogen is made in low-mass stars, but a little bit is made in exploding massive stars. So again, this is largely worked out, but all the details are not. But because the different elements are made in different proportions in different types of stars, it means the composition of the galaxy is changing all the time as the galaxy evolves, different places, different times. And this is happening through what I'll call the cosmic recycling process. Basically, material is cycling in and out of the interstellar medium and in and out of stars. So you have molecular clouds, which are giant clouds of gas and dust in deep reaches of space. They collapse to form new stars. These stars, if they're low mass, become red giants and planetary nebulae and make dust and throw it out. If they're really massive, say 10 times the mass of the sun, they explode as supernovae. And again, most of the material that started in the star comes out, but now it's undergone this nucleosynthesis. So the gas and dust that comes out of the star is different than what went in. And this whole thing goes on and on and on. And what this means is that the composition of the solar system, the composition of the solar system is based on material that had been passed through many generations of stars in the 8 or 9 billion years of the galaxy before the sun formed. And there's been another 4.5 billion years of recycling. So stars that are formed today do not have the exact same composition as the sun. How do we obtain information about this? I've given the broad general idea. And traditionally, of course, part of it is theory, and that's how a lot of it was worked out. But really, in science, you need data. You need to observe nature. You need to understand how it works. And traditionally, of course, the role for understanding how elements are made in stars and how they're distributed in the galaxy is done by astronomy. And this is an astronomy lecture. And I think you'll see that a lot of what I'm going to talk about later is astronomy. It's just a new kind of astronomy. But of course, astronomers do a lot of work with spectroscopy, where you take the light of a star, put it through a prism, and you see these little black lines. Those black lines are where atoms of a given element are blocking the light. They're absorbing the light. And you do a little cross-section through that, and you get these little things, and you can associate that this line is sodium, and this line is, my eyes are bad, so something else. My contacts are starting to reach the end of the day. The point is you can use physical theory of how the star is working and calculate how much there is of the sodium and hydrogen and iron and calcium and so on. So we can use spectra to measure the composition of stars. And this is just an example, and not worrying about the units here, but this is, you can imagine that basically these are all individual stars. On the left side of the diagram are much older stars, and the right end are much younger stars. And you can see that these relative abundances of different elements from the periodic table are different in old stars than young stars. And you can see this change. And this is this cosmic recycling process. You have the next generation of stars getting more manganese than the previous ones, so the manganese to iron ratio goes up, and so on. So that's one way. Oh, and this is I'll get back to this later as well, but you don't have to just do it in optical wavelengths. So this is now an X-ray image taken with a space X-ray telescope called Chandra of a supernova remnant. So this is the remnant of a star that exploded several hundred years ago, and it's still in the process of expanding from this explosion. And this is color-coded. The red, for example, the red here is silicon. So you can see there's these jets of silicon coming from deep inside the supernova and sort of overtaking these other colors, which I don't remember what they are, but they're other elements. So that's the astronomy port. I will show some other astronomical data later. But now I want to switch to what I do, because I'm here. And how else do we obtain information about nucleosynthesis? And the answer is, the way I do it is from meteorites. Meteorites, of course, are rocks that fall from outer space. And this is, I love this woodcut. I don't know, it's just dramatic to me, this falling rocks from the clouds. And I should say, at the time that this particular meteorite fell in France in 1492, it was far from agreed on in the scientific world that meteorites come from outer space. It was known that rocks fall from the outer space, but it was largely believed that they were atmospheric phenomena, that there was some sort of interaction of lightning with clouds making these rocks. Everyone thought it was ridiculous that you could have rocks from outer space. But by the early 1800s, it was well established that, yes, indeed, meteorites must be rocks falling from outer space, and now we've had several hundred years of research on them. Here's a much more modern rendering of a meteorite fall. This is a famous meteorite called Peekskill that fell in fall of 1992, and this was very important because, notice, it fell in the fall, and it fell on a Friday evening in the northeast seaboard of the United States when there were thousands and thousands of people watching high school football games, which means there were a lot of people with their camcorders filming high school football games. And so there's a lot of film footage of this meteorite fall as it went across Pennsylvania, and it landed and smashed into a woman's car in Peekskill, New York. The car apparently had a blue book value of something like $600, but the woman was still very upset. She was a young woman, didn't have a lot of money, till she sold the car and the meteorite to a collector for $30,000, so then she didn't find. But the point is there's a lot of footage of this fireball, which means they could reconstruct where this meteorite started from, and I'll get back to that in a minute. So we see them fall, and it turns out they fall everywhere around the world. There's no real evidence that they fall preferentially in one place rather than another. But they're found preferentially in places where they last longer. So if you see a meteorite fall, and people can watch it well enough to guess exactly where it fell, and it didn't fall in the ocean, you can sometimes go find the meteorite right after it falls. But if a meteorite's been fallen, no one saw it fall, and it's been on the ground, if it falls, a lot of places, within 20 years, the rain will have weathered it away and you won't recognize it. But in the Sahara Desert and other deserts, and especially in Antarctica, it is so dry that the meteorites can last for tens of thousands of years. So it turns out now, most meteorites we have are found in Antarctica, and it's a combination of glaciology and this dryness that makes it that there are good places in Antarctica to just go and find them. And that's a picture of me when I went on a meteorite hunting expedition there in the winter of 2000 into 2001. Basically spent 6 weeks living in a tent on a glacier and riding around on a snowmobile all day looking for black dots in the ice. And when we found them, sure enough, they were meteorites. So it was really fun, and that's a picture of a meteorite that we've just found on the ice. They have this very shiny outside surface because the outside is heated up as they come through the atmosphere. This fireball you're seeing is very energetic. But it's so fast, the heating only goes like millimeters into the meteorite. The interior of the meteorite is very, very cold itself because it's been in outer space for billions of years. So where are they from? We know they're from the asteroid belt, and we know this because of reconstruction of these fireball trajectories. And like I said, like the Peekskill meteorite, you can use photographic records of these falls to triangulate where the meteorite came into the atmosphere and from what direction, and work your way back. And this is an old plot. It doesn't even have that Peekskill meteorite. But the point is that these are a few different meteorites for which this was done. And in all cases, we can say they originated out here in the asteroid belt between the orbit of Mars and the orbit of Jupiter. Asteroids are small rocks, small rocky bodies that are range from meters up to the largest ones that are hundreds of kilometers in size. These are all ones that have been visited by spacecraft of different sizes. Right now, this is an asteroid called Ryugu. Right now has a spacecraft from the Japanese space agency called Hayabusa 2 is investigating this right now, and recently went down to the surface and picked up some material to bring back to Earth for scientists to study in the future. So that's very exciting. This is Eros, very famous asteroid. This asteroid has a moon. This is Ida and Dactyl. So they're interesting. We go and visit them, but they visit us by sending us meteorites. We know from this. And they're very, very important because this is what the solar system looked like, or at least one artist's rendition of what the solar system looked like 4.6 billion years ago when it was forming. And what it looked like was a pancake, a disk of gas and dust rotating around the central star that is growing to become the sun. Now, this gas and dust gradually builds up into bigger and bigger objects. They start with dust, and the dust grains stick together to form a rock, and then the rocks form bigger rocks and boulders, and eventually planets. But not all the rocks formed into planets. We have the asteroids, and comets as well. I'm not really talking about them today. Are leftovers. They're these small bodies that formed from this disk, but they never built up big enough to form real planets, and most of them didn't differentiate into an iron core and volcanic surfaces. And so they contain a fossil record of what the disk was. Some of these meteorites really appear to be collections of what the dust was in the disk that all came together, and very, very little has happened to it ever since. So it's, like I said, a non-biological fossil of this stage in our evolution. And researchers like myself and my colleagues study these meteorites to understand what the conditions were like. How did the planets form? What was the first dust to form? But although most of this dust that we see in the disk, or we see in present-day disks around other stars that are formed in that disk, it turns out some of the dust is from before the disk. It's from previous generations of stars from this cosmic recycling process. And that's what I study. These are presolar grains, presolar stardust. And that's what I'm going to spend the rest of the talk talking about. And this is an old cartoon I made of the process, and it's related to what I showed before. Again, the point is that stars like supernovae, these exploding stars and these evolved stars like the sun will be in 5 billion years, make dust. They make dust. This dust goes into the interstellar medium, becomes part of molecular clouds that collapse to form these disks, that then form planets. And it turns out that some of these dust grains survive trapped to this very day in these asteroids and comets. And we get samples of these asteroids and comets in the form of meteorites. And again, I'm not going to talk about interplanetary dust particles. They are very, very tiny meteorites that we collect in the stratosphere, and a lot of them seem to come from comets. And we see presolar grains in both of these types of materials. So these are dust grains that formed in stars. They're actual pieces of stars we can study in the laboratory. So this is a very, very famous song lyric. I've seen volunteers for this lecture series that says, "We are star stuff on the back." Very famous song by Joni Mitchell, but it's literally true that the atoms in our body, or a large fraction of the atoms in our body, came into the solar system originally as dust. And we actually can see some of those dust grains now. So how in the world can we possibly know this? And the answer is with isotopes. And for people who don't remember their middle school, high school chemistry and physics, I will remind you that the atom, everything's made of atoms, has a nucleus where most of the mass is. It's positively charged, surrounded by a little cloud of electrons. The nucleus is made of neutrons or protons and neutrons, which are almost the same kind of particle, except that the protons have a positive electric charge and neutrons don't have any charge. What kind of element it is based on how many protons it is, the atomic charge. So every carbon atom has 6 protons. But about 1 out of every 89 carbon atoms on the Earth has an extra neutron. So most carbon atoms have 6 and 6, but 1 out of 89 has an extra one, and we call that carbon-13, because it weighs 13 in these units compared to 12. There's also carbon-14. I didn't put it on here. This is a radioactive isotope. It's very, very important for archaeology, for dating things, but it's radioactive. It's made all the time in the atmosphere by galactic cosmic rays coming in from outer space and breaking up nitrogen atoms. And so it's a separate thing, but it is another isotope. These are both stable, and like I said, on the Earth, or in the solar system, there's about 89 carbon-12 atoms for every carbon-13. Some places it might be 88, some places it might be 90, but it's a pretty narrow range. And so if we look at that on a histogram plot, this is the solar system on this graph. Plot's right here. And I've plotted it over several orders of magnitude, several factors of 10, so a ratio ranging from 1 to 10,000. And you'll see why in a second. But pretty much everything in the solar system lies on this one line, or most of the solar system. But when we put on grains, these are microscopic little bits of dust of silicon carbide, which is an unusual, high, very, very refractory, hard phase. If it's familiar to anyone, it's probably because you've bought sandpaper made out of this. It's a very hard substance. And it turns out it's also a presolar phase. And so this is a picture of a 1 micron grain of silicon carbide found in a meteorite. And we can measure the carbon isotopes in individual grains like this. And when we do, we find that the grains are not necessarily 89. A couple of them are. But in most of them, the ratio is very, very different from 89. Some of them, the ratio is as low as 3. In others, it's 100 or 200 or 1,000, or the highest ones are up close to 10,000. So this is a huge range in isotope ratios that is completely distinct from what we see in the solar system. And the only processes we know of in nature, in physics, that can make such wide ranges of the isotope ratios are nuclear processes. And the only place in nature, really, where you have nuclear reactions occurring on a regular basis is in the deep interiors of stars, what I talked about earlier. What is powering the stars is nuclear reactions. And it's that nucleosynthesis itself. While the hydrogen is burning into helium in the core, it's also changing the carbon-12 into carbon-13. And that's what we see here in these dust grains. So we can already say, just on the basis of nuclear physics, that these grains can be associated with stars. But we can do more than that, because in some stars, you can actually use astronomy to measure the isotope ratios. It's not that common. You need special types of stars. You need only certain elements. You can do it, but in some cases, the spectral lines are just enough separated from each other for the different isotopes you can measure it. And astronomers have done this for a certain type of carbon-rich AGB star. And when they measure the carbon isotopes in these stars, you see a very, very similar distribution to what we see in these grains. So this is strong evidence that not only do these grains come from stars, but they come from this kind of star. But we can measure, so I'll come back to how we actually use the data more. I want to give a little more general background on these. These are some pictures all taken with electron microscopes. So instead of telescopes, and I'll get to this, we use different kinds of microscopes. And these are all taken with scanning or transmission electron microscopes, which allow you to look at things at very, very small scales. And these have been discovered for 30 years or so we now have a large number of kinds we've discovered. The first ones that were really well discovered were well characterized were silicon carbide and graphite. And the graphite is like pencil lead. They're little balls of carbon. They have different structures. This is a graphite grain that somebody used a diamond knife to cut a thin slice through. And when they did and put it in the electron microscope, they discovered at the very center, there's a very dense grain. That's a completely different mineral. That's a titanium carbide phase surrounded with this graphite. So it's multiple phases that all formed in a single star. We see glass, we see silicates that are familiar, like the rocks we see on the Earth. We see aluminum oxide, which is a ruby or a sapphire. So we have all kinds of different grains that we can now, and because they have different chemical compositions, we can measure different kinds of isotope ratios and use them to learn something about the parent stars. Before I get to how we do that, I want to emphasize that these are really small. So this is an optical microscope image of a human hair, which is about 1/10 of a millimeter across. And this is one of the largest presolar silicon carbide grains I've seen. There are some that are bigger, but the vast majority are much smaller. This is about 5 microns across. And you can see compared to a hair, that's very, very small, but you could see it in the optical microscope. This is a much more typical size for the presolar grains, especially the presolar silicates. And that's, on this scale, is 10 times smaller in diameter, but that means it's 1,000 times smaller in the number of atoms. So these things are very, very small. And this whole field has been made possible by the fact that there have been enormous advances in microanalysis, nanoanalysis technology over the last few decades. This is largely driven by the semiconductor industry. We want to cram more and more transistors onto silicon chips. You need to be able to characterize your silicon extremely well. You need to be able to get in there and make sure everything is exactly as you want. So I'm going to describe what some of the methods we use for analyzing these. And they're not all from semiconductors, but basically modern science and nanotechnology really drives a lot of the development of this instrumentation. So this is really a new type of astronomy. We're able to study stars by taking little bits of solid bits of stars, and putting them in the laboratory. So what are our telescopes? Well, they're of course not telescopes. They're, as I said, they're microscopes and other analytical tools. Most of my own research has been based on a technique called secondary ion mass spectrometry. And the basic idea here is you have your presolar grain or your meteorite or your rock or whatever, and you blast it with a beam of ions. You focus a beam of cesium ions or oxygen ions down to very, very small beam, and you hit the sample with it, and it knocks atoms off. It's like sandblasting a surface to clean a brick wall. You knock these atoms off, and some of these atoms come off in just the right way that they can then be put through what we call a mass spectrometer, which is just a device that uses electric fields and magnetic fields to weigh things. So we can knock the atoms off, and we can say, oh, that was a carbon-12 atom. Oh, that was a carbon-13 atom. And in that way, determine an isotope ratio on very, very small scales. So this tool has been essential for this because it allows us, the first generation of these allowed us to measure things at the 1 to 2 micrometer scale, some of those bigger grains I showed. And the current one, like the nanosims, and this is a picture from our lab in Washington, D.C., this is a commercial instrument built by a company in France called Carnegie, and it allows us to measure things at the 100 nanometer scale. This is very, very small, and that's where these grains are. So the fact that we can measure them is based on the development of this really advanced technology, which I'm very grateful for. So a lot of the data I will show you and that we have in this field is based on this. There's another very, very interesting new device that a group has built at the University of Chicago. And whereas the instrument I showed you just now is a commercial instrument, this is a home-built instrument, largely funded by NASA. And it's a collaboration between the University of Chicago and Argonne National Lab, which is near Chicago. And this uses lasers to blast your presolar grain to get the atoms off of it, and then shines other lasers through the atoms that come off in just the right way that you can measure a specific element. And this is very, very useful for measuring very, very rare elements and heavy elements. And I will show a little data of that later. So when I say RIMS later, this is what I'm referring to, this instrument. We also can study not just their isotope composition. There's also a lot of information in these grains from their chemical composition and in their structures, how the atoms are lined up. And a lot of this work is enabled by the development of transmission electron microscopy in particular, where you take a sample, you might have to make it very thin to begin with, and then you shine a beam of very, very energetic electrons through it. And the way the electrons interact with the sample can tell you what the sample is made out of, it can tell you what elements are there, and it can tell you how the atoms are lined up. And these are just some pictures where you can actually see individual atoms and how they're lined up in the sample. And this can be very useful for understanding how these dust grains form. And I'll give some examples of that later. So I want to mention the presolar grains. Not only are they small, they're also very rare. This shows the abundances of different types of presolar grains in meteorites. And what we see is they're typically on the order of, at most, 100 parts per million of the meteorite. So these are a very, very tiny fraction of the meteorite. Most stuff in meteorites is not presolar grains. So, but over the years, we've developed ways to find these very rare things. I don't have time to go into those methods, but they are very useful, so now we can find what we want, though we're always searching for new types of grains and new methods to find even more. So what are these good for? What are presolar grains good for? It's really cool, we have them in the star, but why keep studying them? Are they just an oddity or are they useful? And it turns out they're very useful probes. To show this, I want to just mention that all the grains I'm going to be talking about formed, and because most of the grains we have, we think came from two types of stars. AGB stars, which I've mentioned before, and I'll get into that again in a second. It's an acronym that astronomers invented called asymptotic giant branch, and you really don't need to know that. All you need to know is that AGB stars are the almost end stage of a star like the sun, or a few times as massive as the sun. So in 5 billion years, the sun will run out of hydrogen in its core, burn helium for a while, and then become an AGB star with a core made out of carbon and oxygen. And it will throw off its outer layers, most of the mass, in a wind, which includes dust, and then the dust will reflect the light, and that's the planetary nebula, leaving behind, eventually, the core becomes a white dwarf star that just will cool for the rest of the evolution of the galaxy. Unless it was in a binary companion with something else, which could lead to all kinds of other interesting phenomena, but that's for a different talk. At the other end of the spectrum, if you have a star that's, say, 10 times the mass of the sun or more, it has a much different life cycle. It burns hotter, it burns faster, it burns to much heavier elements than just carbon and oxygen, and eventually explodes, and gives out lots of energy and makes dust. Both of these make dust. So I'm going to start with the AGB grains and give you a little idea of the history of these presolar grains and why they're useful. So before there's even a presolar grain, say 7 billion years ago or so, oops, let me go back for a sec. 7 billion years ago or so, a star maybe 1.5, 2 times the mass of the sun formed. And then it spent the next 1.5 billion years, 2 billion years, burning hydrogen in its core, just like the sun is doing. But because it's more massive than the sun, it burns faster. So it doesn't last 10 billion years, it say lasts 2 billion years. And eventually becomes a red giant when it runs out of hydrogen in its core. And then it burns helium. And then when all the helium is burned, it becomes this AGB star. And it's at this stage that you really have this wind leaving the center of the star. And as the wind cools, as it gets farther away, the gas cools. And when it gets below about 2,000 degrees, the atoms can start condensing, sticking together to form dust grains, like silicon carbide and olivine and minerals that we know in the world. And after that, eventually, it becomes a planetary nebula. And a planetary nebula is just all the dust that the AGB star made, now surrounding this white dwarf star and being lit up by the radiation from that star. So they're beautiful things, but what they are is a whole lot of things that could eventually be presolar grains in another solar system, when you see those beautiful colors in a planetary nebula. Well, so those dust grains leave the planetary nebula, and then they're in the interstellar medium for some period of time, maybe 10 million years, maybe 1 billion years, but in this case, probably 100 million years or something. And during that time, these grains can be hit with high-energy radiation coming out of supernovae. They can hit other grains. There can be collisions between grains. The grains can be destroyed. They can aggregate to form new grains. All kinds of things can happen in the interstellar medium. Eventually, they become incorporated in a molecular cloud, and eventually that collapses to form a protoplanetary disk and as I said, some of them will end up in asteroids and comets that come to us as meteorites, and then we measure as presolar grains. The key point is that presolar grains are witnesses to all these stages. They're witnesses to this stage because they bear the isotopic signature of the nuclear reactions that were happening during this stage. They even bear the starting composition of the star, so we can learn even about how this star got its composition. So presolar grains are useful for probing processes that occur throughout all of these things, from stellar evolution, how the elements are made, how dust is made in stars, how dust is processed in the interstellar medium, how dust gets into planets, and so on. So they're very, very useful. And I'm going to spend the rest of my time giving examples of how we use these grains and to learn more about different processes on this list. So, as I've already mentioned, we believe that most of the presolar silicon carbide grains, and I already showed this picture in this plot, we believe come from this kind of AGB star. And the main reason for this is based on direct comparison with astronomical observations. In this case, we can compare the carbon isotopes we measure in the grains with the carbon isotope ratios measured in the stars. But more than that, it turns out when you look at these same types of stars at infrared wavelengths, this is now at 10 micrometer wavelengths of the light, you see they often have this little bump out here. So this is the tail of light from the star, which peaks at much shorter wavelengths. And we see this little bump. This bump is known to be due to little tiny silicon carbide grains that have formed in this AGB star. and are absorbing light from the star and re-emitting it at this temperature. And we know this because we can measure silicon carbide in the laboratory, how it emits infrared light, and tell that it does. So we know that these stars have this carbon isotope composition and make silicon carbide. We have silicon carbide grains with this composition. Therefore, they come from this kind of star. That's the first step in understanding where these grains come from. But, okay. But the grains can tell us much, much more than just that they come from these stars. And the reason is that we can measure elements and isotopes that cannot be measured by telescopes. So once we establish this grain came from this star, we can measure other things and learn more about those stars that we cannot find out with astronomical observations. And so I mentioned this earlier in this plot. So on this color-coded plot, dying low-mass stars are AGB stars. Maybe I should have just called them that, DLM stars or something. But the point is, these make carbon and nitrogen and a lot, you see all this orange color here, they make a lot of the heavy elements. This has been known for a while, but the details of how this is done is not that well understood. There's a lot of astrophysical models, people trying to make computer simulations of these stars and put in all the physics as best we can to explain how you make these elements, but not all the details are known. And in some cases, there are parameters we just don't understand, and having more data would help. And that's where presolar grains come to the rescue, because there's just a huge number of these things that cannot be measured by telescopes. So I'm going to start with one example, which is an isotope called aluminum-26. Now, all of the aluminum atoms you ever see on the Earth, in your soda can, or whatever, are aluminum-27. Aluminum has only one stable isotope, and that is 27, which has 13 protons and 14 neutrons. But stars make aluminum-26. It has a half-life of 720,000 years. And within that 720,000 years, or after 720,000 years, half of the atoms turn into magnesium-26. And they do so by having a proton turn into a neutron. It's a process in nuclear physics called beta decay. And it emits something called a positron, which is a positive version of the electron, and turns into a magnesium-26 atom and emits a gamma ray. And this is very important astronomically because this gamma ray can be detected by telescopes. And this is a map of aluminum-26 right now throughout the galaxy. And you can detect it, and you can tell where aluminum-26 is being made. So this isotope exists in nature. It doesn't exist on the Earth because when the Earth formed 4.5 billion years ago, and all the aluminum-26 it might have had at the beginning has long since faded away. But we can find a fossil record of it in meteorites. It's very important for a lot of meteorite studies because the early solar system had aluminum-26 in it. I'm not talking about that. I'm talking about presolar grains. But where it's also very, very important. And here, so on the left is the relative proportions of the 3 stable isotopes of magnesium, and this is a logarithmic scale. So you actually have about 10 times more magnesium-24 than magnesium-25 or magnesium-26. And the sun also has about 10 times more aluminum than, magnesium than aluminum. In these presolar grains, when we measure them, we often find that they have a lot of aluminum, and their magnesium is almost pure magnesium-26. And when you see a single isotope just sticking up like this, like a tree in a diagram like this, it's usually a sign that it's radioactive decay, that this isotope used to be a different element. And in this case, we can tell that these magnesium-26 atoms, when the grain formed in its star, they were actually aluminum atoms that decayed once the grain existed. And we can tell how much from how much magnesium-26 is there. So we can do this, and this is now a plot. I'm not going to have too many data plots, I don't think, but this is now a graph that shows the amount of aluminum-26 in these grains that we can infer from the magnesium, plotted against their carbon isotope ratio. And these are all silicon carbide grains we think came from different types of AGB stars. That's why they're different colors. It doesn't matter. But we can see that typically we find about 1 part in 1,000. 1 atom in 1,000 of the aluminum was aluminum-26. But okay, that's interesting. What does it mean? Well, it means we can compare that to theoretical predictions, that people can make predictions with their computer models of how much aluminum-26 an AGB star should make. And these are all models of different masses of AGB stars with different assumptions. And we can see that, they kind of overlap with the data, but not perfectly in detail. And I don't want to get into why and where, because we don't really know everything yet, but the people who do this modeling love these data because there's no way to get this kind of data any other way. We know this grain was in an AGB star, and if a model is going to explain that AGB star, it must be able to predict that that's the amount of carbon it has and amount of aluminum isotopes. And so at some point, the data will help get the models much, much better. We can do this for other elements as well, and again, don't worry about, there's a lot of symbols and numbers and things I'm not going to explain. These are barium isotope ratios. The key point is here, the black points are measurements of the grains. These use this instrument, this RIMS instrument I was talking about. This is the only way to get this kind of data. And this is amazing that you can measure the isotope ratios of a barium atoms in these grains, because barium is only some tiny, tiny fraction of the grains of the atoms in this already very, very tiny grain. So this technique helps us do these measurements. And these symbols are all different models of AGB star predictions for different parameters, different things that are not well understood about the model. So they calculate the predictions for sort of a range of ideas so we can see which work best. And what we can say is, for example, these blue symbol, that model completely misses the data. Most of the models sort of hit the data, but these don't. So we can immediately say, AGB stars do not act like this model, and we should stop thinking about this kind of model. So it's this way these grains are extremely valuable for understanding how these heavy elements are made in stars. And there are a number of expert nuclear astrophysicists around the world who do this kind of modeling, who just love these grains because they have real data they can analyze. And we can test these theories with very high precision, especially in the context of astronomy, where sometimes getting small error bars is very difficult because you're trying to do things with very low signals from light. And here we can have the grain in the laboratory accurately count the atoms. So it's a very useful complementary technique to astronomical observations. I want to switch now to other grains from AGB stars, and this is now a plot of oxygen isotope ratios. Oxygen has 3 stable isotopes. Most of the oxygen is oxygen 16, but there's small amounts of oxygen 17 and 18. And just as we saw with the carbon, the solar system sits right here at this crosshairs and very little around it. I'm plotting this on scales, over many, many powers of 10, many orders of magnitude. The green symbols are oxide grains like aluminum oxide and magnesium aluminum oxide, and the red symbols are silicate minerals like olivine and pyroxene and quartz. And what we see is the grains don't fall everywhere, they fall into patterns. They're extremely different from solar. These are presolar grains. They have to be from stars. And we can do the same thing we did with the silicon carbide. Turns out you can measure oxygen isotopes with large error bars, but you can do it telescopically in AGB stars. And when you do, you see that the stars overlap with most of the grains. Most of the grains, like 80% of the grains, actually lie up in this region. And so already it says, these grains probably come from this kind of star. We can also compare to theoretical models of these stars, and they predict this same kind of range of compositions. So we have a good idea that these grains come from these stars. Now, there's grains over here that don't come from the AGB stars and cannot be explained, and we think all these other ones over here come from supernovae. These ones up here have too much oxygen-17 to be from AGB stars, and the current thinking is they're from something called novae, which is an explosion that's much smaller than a supernova. We don't know for sure. We think these are from AGB stars, but from a special type with special mixing going on that is not well understood. So we can sort of understand the basic idea, but we know that most of them come from AGB stars. Now, instead of nucleosynthesis, I want to talk about how these grains can be useful for just understanding dust itself. And dust is very, very important in astronomy. To many, many, many astronomers, maybe most astronomers, dust is a nuisance. It is something that is everywhere, and it's blocking light and changing light that they want to see. So they want to observe this galaxy that's 100 gajillion light years away, and in between that is 100, 200 gajillion dust grains that absorb some of that light and make it harder to understand what you're seeing. But plenty of astronomers are interested in the dust in its own right because it's part of nature and trying to understand everything that's made, everything that happens in the cosmos. And as I already showed the spectrum earlier for silicon carbide, when you look at oxygen-rich AGB stars, you see different spectral features in the infrared. And in particular, you very commonly see these features at sort of 10 and 20 micrometers that are due to silicate grains. But it's very hard to tell what kind of silicate grains. You can look at the shape and compare it to laboratory data. But the fundamental problem is that when you measure a spectrum like this of a star, you're measuring the average of a huge, huge number of grains that are all in the beam of that light you're looking at. The star is a point source, so you're looking at a huge number of grains. Well, presolar grains have the obvious potential for telling us more because we can tell each individual grain if we can learn what its mineralogy is and do that for a large number of grains. We can then start comparing to the stars and say, this is really what AGB stars make, this kind of dust, and then that can help interpret the spectra, and hopefully we will iterate towards better understanding. So how do we study the mineralogy of these very, very small grains? We take advantage of a device developed, again, in the semiconductor industry called focused ion beam. And this lets us, for example, this is now a scanning electron microscope image of a meteorite, and you just see all these little dust grains. This is probably a few microns across. And we've decided there's a presolar grain right here. What do we do with it? Well, we actually use this ion beam to come in and cut it out of the sample, and we can cut out a thin little wafer. So this is a wafer that was through the grain, was inside here. And then we've welded it to a little needle and pulled it up. This is all happening at a few micrometer scale. Its technology is just mind-boggling. And it was developed originally for the semiconductor industry to do things like cut wires on microchips. So if they're developing a new circuit, they don't have to refab the whole chip. They can just change the wiring by welding in a new little wire and cutting this one. And it turns out it's extremely useful for other things too, and a lot in geochemistry and a lot of rocks now for pulling samples out of rocks to measure. And then once you have that, you can, for example, put it in the transmission electron microscope and see what it looks like at very, very small scales. So this is now we're getting down to nanometer resolution on these grains. So again, TEM can tell you a lot. These are complicated. I'm not going to go into too many details. This is work from Ann Nguyen at the Johnson Space Center in Texas. And she found a very interesting little thing where she found 3 presolar grains right next to each other. And she went in with the fib and made a section through it. So you can see these are all grains. These are now imaged in the microscope, and they all look different. And you can see this one is kind of patchy, but this one has these lines going through a striation. Those are crystal planes. And you can do something called electron diffraction, which is looking at how the electrons scatter off the atoms. And you make these little dots, and by interpreting where these dots are, you can reconstruct the crystal lattice, how the atoms are lined up, and tell exactly what kind of grain that is. And you can see that this grain is amorphous and this is crystalline. They were made in the same star, probably. These are elemental maps, so you can make element maps, not isotope maps, but element maps on very, very small scales. So you can do this kind of thing. And these are just a few examples. Here's a grain that is a few hundred nanometers across, and the green shows where silicon atoms are, and magnesium shows where magnesium atoms are, and you can see that the composition of this grain is changing on a sort of 20 nanometer scale as you go through here. This is another crystalline grain with a diffraction pattern. The takeaway here is that now that we've done this, and this is very difficult work, so it takes a lot of time, and so even though it's been doing this for years and years, we've been doing this for years and years, there's still only maybe 20 or 30 grains. But what the picture we're getting is that these grains show a huge diversity of different types. They're not all the same. They're, in fact, mostly all different. There's some, we get some groupings of a certain mineral, but mostly everything seems to be different. And this is bad news for astronomy for interpreting spectra because it's very hard then what's the average of things that are so different. But we're working on it, and we still need to get a lot more data. But what we know is stars make far more diverse ranges of dust than has already been known or believed from observations, as well as theoretical predictions for how dust forms in stars. And that the nature is finding interesting things to do far beyond our imaginations so far, and these grains are helping us understand that. I want to show one more example of AGB stardust, because this is important for another type of science investigation. So these are 2 presolar aluminum oxide grains. Like I said, these are known to most people more in their gem form of rubies or sapphires. And, but the mineral name is corundum. But these are 2 grains. They come from AGB stars from their oxygen isotopes. And we took fib sections and look at them in the transmission electron microscope. And what we see is this one has these giant cracks going through it. And this one, you can even see it here, has a little bite taken out of it that is almost certainly an impact crater, probably in interstellar space. So these are probably recording collisions of dust grains between the time these grains formed in the star and before they were incorporated in the meteorite, either in the interstellar space or in the protoplanetary disk, though it's more likely in interstellar space because that's where the grains are more likely to get accelerated relative to each other to high enough speeds that they could do this kind of damage. This is a really hard material. And so I think we're looking at sort of a snapshot of dust grains being destroyed in the interstellar medium 5 billion years ago, and we can study it in the lab. It's pretty profound. Now I want to switch for the last little bit of this talk to supernovae. I've already mentioned them. This is a before and after shot of a very, very famous supernova, 1987A, which occurred shockingly in 1987. And it's very, very important because it's in one of the Magellanic Clouds, which are very, very close galaxies to the Milky Way. This is so close by modern astronomical methods that we can study this with every telescope at very high resolution, and it's just getting better and better. Point out that in my new units, the amount of energy released in the supernova is about 10 to the power of 42 M&Ms. They put out, that's very energetic, trust me. This is what it looked like by the Hubble telescope a few years after the explosion, and you can see these rings of material that have expanded from the original explosion. So supernova dust is of great interest to astronomers, and the main reason is that dust is observed in galaxies that are very, very far away, what we call high redshift galaxies, that are very young galaxies. And they're basically so young that there hasn't been enough time for low mass stars to become AGB stars and make dust. But these galaxies have a lot of dust. So the thought is the dust must come from supernovae. But decades of observations of supernovae that are closer to us were very unclear as to whether they could observe dust. And so it's been very controversial for years how much dust is made in supernovae. It's still hotly debated. But the game has changed in recent years with the development of several new advanced telescopes that measure long wavelength light. For example, the ALMA famous array of radio telescopes in South America. This is an image of supernova 1987A at 450 micron wavelength, what we call submillimeter radio. And this little blob of light there is emission from dust grains that formed in this supernova and now have cooled down to low temperatures. So we have evidence that grains form in supernovae. We don't. The real question is whether that dust survives. And the reason is that this shock wave from the supernova is still moving out, but at some point it's going to bounce off the local interstellar medium, and there's going to be a reverse shock wave that goes back into the middle. And there's a lot of theoretical discussion that shock wave could go in and destroy all these dust grains. So one question is, this shows supernovae make dust, but does that dust make it into the cosmic recycling process I discussed before? And we can say, well, it must to some extent because we have presolar grains from supernovae. So we know supernovae make dust, at least some kinds of dust, because we observe it. And it's some fraction of all the different types of dust grains that we observe. How do we know this? And it's based on another radioactive isotope. And this is an example from about 20 years ago. This is the smoking gun paper, where we basically measured calcium isotopes, and this is a graphite grain. And the calcium isotopes is just like that pattern I showed before magnesium. These lighter isotopes of calcium 42, 43, this is all relative to 40, are normal, and it had more than 100 or 200 times more calcium 44. And this is a clear sign that calcium 44 started as titanium 44. Titanium 44, it decays very similarly to aluminum 26, becomes calcium 44, but it has a half-life of only 59 years, and it is only made in supernovae. So this grain formed with titanium 44 live in it. It had to have been near a supernova, so the only real explanation is it formed in that supernova. And interestingly, after we measured it, we looked at it again, and we had removed the surface layers, and we found that inside the grain was a titanium carbide grain. So that titanium 44 was probably in this little crystal inside the graphite grain, which is really neat. But it's not just the titanium 44. That proves it, but we can measure 10 different isotope ratios, 20 different isotope ratios of different elements, and for the most part, they all point to a supernova origin. And so we have a very good understanding, or at least belief, that these come from supernovae. So what are these good for? Other than, I already told you, they tell us the profound thing that supernovae do indeed make dust. And again, without getting into any details, we can use them as probes of nucleosynthesis. We can compare, in this case, we're comparing two grains to a predicted pattern of molybdenum isotopes. The basic pattern is the same, and it tells us about a certain kind of nucleosynthesis that might happen in supernovae. So that's interesting, and there's a lot of examples like this. I don't want to go into any details, but they're very valuable for this. One thing that's very interesting is they tell us about mixing in supernovae. And before a star explodes as a supernova, it's thought to have this sort of onion-style structure. This is very schematic, but it's probably fairly realistic at some level. Whereas you go deeper into the massive star, you reach layers that have experienced more and more history of nuclear burning and have heavier elements. And what we find is to explain the data we find in the grains, to explain the titanium 44 is made very deep in the star. But the carbon, where you need to make silicon carbide, is out here in the helium burning shell. And somehow you have to mix that material. This is very, very important and also very difficult to quantitatively understand. But there's observational and theoretical evidence that this must happen. These are the results of very sophisticated computer simulations of mixing in supernova ejecta. Hydrodynamic models on supercomputers where I It's not my work, so don't ask me to explain it in any detail, but the point is you can see these little blobs coming out, you see these instabilities mixing material. And I already showed this plot. This shows that at least it's not all just coming out in layers, that you have like jets of material. But neither the observations or theory are anywhere close to getting down to the microscopic scales we need to explain these microscopic dust grains. We're a long way from tying what we see in the grains to what we understand about supernovae. But we have real data that must eventually be explained, and they will be valuable as computers get more and more powerful and better, and telescopes get better at observing supernovae to get a better idea of how these things happen. And the final thing I want to talk about with supernovae is we can also look at their structures to see how dust forms in supernovae. We really don't understand what kinds of dust form, how it forms. This is a very interesting graphite grain we found. This is in the transmission electron microscope, and you see it has two morphologies. It's again, a few microns across. It has a very tight core, a very dense core, and then it's surrounded by these sort of thin layers of graphite just grew on it. And when we look at an oxygen map, this is an isotope map, and where it's bright, that means there's more oxygen-18. You can see that as this grain was growing, all of a sudden it grew with a lot more oxygen-18 and then stopped again, and then the oxygen-18 went down. We don't know why this is, but it probably, this grain was growing and moving through the supernova ejecta, and it just happened to hit a patch of gas that had more oxygen-18. So this is incredibly detailed. This is a tiny, tiny grain of titanium carbide, again from inside a graphite grain. And when you look at it, you see this very faint gray rim around it. That's a sign that this grain was, before it was in the graphite, it was by itself in the supernova, and it was irradiated by high energy radiation, just bombarded by radiation from the supernova that made this rim. So this is, again, telling multiple histories of just growing this one microscopic dust grain. This is a more recent example of the silicon carbide grain, and where the TEM showed their subgrains of iron and titanium carbide, and this is just showing we are now at the point where we can even measure the isotopes in these individual tiny little titanium grains. This is an isotope ratio map. And again, without the details, the point is that by analyzing these, we're now at the point where we can analyze the same tiny bit of material in multiple instruments and really correlate it, and that's what this is and what this is, and it's really kind of profound. And it's telling us that supernovae, that while dust grains form in supernovae, the conditions are just changing very rapidly. The pressure, the temperature, the composition of the gas to explain all these things. And it's very complicated, and we're nowhere near an understanding, but it's there. So I have one more very brief topic to discuss, and then I'll be done and can take some questions. I want to finally say we can also use presolar grains to say something about evolution in the solar system. And for this, I'm bringing back the fact that we also have comets. And when you look at this protoplanetary disk, the asteroids formed fairly close to the sun, and within a few, say, 5 or 6 times the distance of the Earth from the sun. That's where the asteroids formed. The comets, which have these spectacular tails, formed much farther out. They have much more ice in them. Asteroids don't have a lot of ice. Comets are sort of half ice. The reason you see these tails is when the comet comes close to the sun, the ice sublimates and blows jets of dust out behind the comet, which then reflects the sunlight. As I said, we get IDPs, interplanetary dust particles we collect from these and can study in the laboratory. And we get meteorites from asteroids. And basically, the cometary IDPs, the ones we found, seem to be extremely pristine. They're little aggregates of tiny bits of dust that from the disk that nothing really has happened to at all. The meteorites are also collections of dust that formed in the disk, but they've often seen a little bit of processing, that their asteroid got heated up enough that what ice it had melted and turned into water and sometimes reacted with the silicates and made clay minerals and this kind of thing. Or they were heated enough not to melt and become something different, but enough to erase some of the original chemical signatures. And disentangling this is a big part of what cosmochemists are trying to do, is to understand what these different meteorites and their range of processes mean for the evolution of these early small bodies that grew into planets. And understanding the relation between comets and asteroids, because they're all forming from this disk, the main difference being where in the disk they are. And presolar grains can be useful in this because some of them are very, very sensitive to this processing that may happen on a parent body. So a little bit of this, if this ice melts and the water reacts with the silicates, it can destroy these presolar silicates and we'll never find them. So we can use the silicates. And this is just one brief example of this. What this is a plot of something versus nothing. So each row here represents a different meteorite. and IDPs, and how much presolar silicates is in them. And what we see is that the different meteorites vary over and this is an old plot. I need to update it. We have some that are much smaller as well, but pretty much up to about this value. The highest we see in meteorites is about 240 parts per million, and comet dust, IDPs, can be up to 1%. So there is much higher abundances of presolar silicates in cometary dust than in meteorites, and we think this is reflecting processes happening both in the protoplanetary disk before this stuff comes together to form the meteorite, and in the parent body, in the asteroid, before the meteorite comes to Earth. And so we can use these in detailed ways and start comparing them to other geochemical observations of the meteorites to try and correlate, in the hope that eventually we might use this as a very quick test of a meteorite. Is this really primitive and worth spending some more time on? And this brings me to my last science slide, which is because, as John said in his introduction, today was a big day for me, completely accidental. It happened the same day I was coming to give this lecture, but we had a very exciting to me, paper come out in Nature Astronomy today, where we found this little blob of carbon-rich material inside a meteorite. So this is now a meteorite from an asteroid, and when we, by luck, found this little thing, it's about 100 micrometers across, a tenth of a millimeter. Very, very rich in carbon. And in fact, in all ways we can find, it looks very much more like a piece of a comet than an asteroid. And one way it does is that it has much, much higher abundances of presolar grains than typical meteorites. So we think this is a bit of comet dust that it either never was in a comet, or it was in a comet and then got ejected from the comet before this asteroid came together, got collected by this asteroid farther in the solar system, and then became part of the asteroid, and then was delivered to us in a meteorite, and then we went and destroyed it with all kinds of techniques, and all in the name of science, but I think it's worth it. I don't think carbon-rich clasts and meteorites have feelings, but I hope not. In any case, this is the last thing I wanted to show. Basically, I hope what I've explained to you and convinced you is that we have actual solid bits of stars, for presolar stardust, in the laboratory. We can take advantage of really advanced nanoscience technology to analyze these down to the atomic level and really learn new things about the cosmos that it's not possible by any other way. So it's really a new form of astronomy, very complementary to other astronomical techniques, that's really helping us better understand this periodic table in the International Year of the Periodic Table of the Elements. And with that, I will say thank you and take any questions.
Okay.
Thank you.
We have a mic if we have some questions.
Let the people run who have to run.
What's that?
It's to let the people run who have to run. And
Yeah, no. There's a lot of movement.
yeah, I went too long.
Yes, I have one question. There's one meteorite that I think would be interesting, is the Tagish Lake meteorite
Yes.
that fell. Did you do any research on that one?
I've done a lot of work on Tagish Lake, but not so much in terms of presolar grains. I found it to be more interesting in terms of the organic matter it contains. We've done some very interesting work on that may be very important for understanding the original sources of carbon on the Earth, prebiotic for prebiotic chemistry. There has been some studies of this meteorite for presolar grains and show it has similar amounts to other meteorites of kind of similar types. But it's not particularly special in terms of the presolar grains.
Oh, because it was very...
But it's very special
like
in a lot of
one-of-a-kind,
other
yeah.
methods. I'm sorry?
It's a one-of-a-kind, it seems like. Has there been any other that have been discovered that are like that one?
Like Tagish Lake?
Yeah.
Not exactly, no. Right now it's a unique carbonaceous chondrite.
Excellent, thank you.
So, and it was also, for people who don't know, this is a meteorite that fell on a frozen lake in Canada in the middle of winter, and there was someone who saw it fall and went and collected it and kept it cold. So it's the only meteorite we know that was collected cold and has been cold ever since. And so that's why it's really interesting for organic chemistry, because there's organic molecules in it that would have left if it had been heated up, and we can really tell what it had. So it's really exciting.
We have a question over there.
Yes, hi. Thank you so much. This was so interesting. And I have a question regarding the process of flattening the presolar grains. So you had mentioned that you flatten them. Once you have them, you were showing the tiny particle that it is compared to a hair. And then you said that you flatten them. And I wondered what that process was and if it actually damages. And then you said you damage some of them. So how does it work?
I'm not sure what I said that sounded like flattening. We don't flatten the grains. We find them, we measure them. We do, in the course of measuring them, and maybe this is it, this method I said of SIMS, which we blade away, that has that's basically taking away the atoms layer by layer, so that will tend to flatten them. But I'm not really sure.
That's probably what it was. And in that process, then, when you're shaving away the grains, are you destroying it? I mean,
yes,
what happened?
unfortunately, the only way we have not found a way to determine the isotope ratios of a rock without actually destroying it to count the atoms.
But then you're able to see the different layers of each
Right,
grain
so
in there.
it depends on what technology we use, and it's getting better and better. It used to be we would have to destroy the whole grain to measure 2 elements. Now we can destroy a little bit, or we can image across and see how it varies. So it's getting better and better, but there's always the possibility, that if it's heterogeneous, that we've measured this layer and this layer is different, and the only way to ever know for sure would be to measure the entire thing.
Okay, and is that where the fib comes in as well, the little cutting out?
So we use the fib, that's really destroying it, but we're using that to make a thin sample of it that we can then use in the transmission electron microscope, because it requires thin samples.
Cool.
But that's perpendicular to what we look at it with the SIMS from this direction. The fib looks at it from this direction, so that way at least you're getting 2 different cross sections, and you can get information about the grain that way.
Very cool. Thank you.
Is presolar dust expected to be found also in planets already, say deep inside the mantle of Earth?
No, and the reason is that the grains are destroyed by high levels of heating. So if you start having differentiation of the planet, you're going to heat these grains so much. The silicon carbide, for example, would react with the other silicates. The atoms will all melt and go together, and you lose all record of it. So we don't expect them to survive at all in planets. They have to be in these pristine meteorites that have had no geology happen, basically.
Okay, thank you.
Thank you very much for your lecture. I've got a question about your half-life of aluminum 26 to 27. You said they've got a half-life of 750,000 years.
Yes.
Why we even see any of aluminum 26 left in your sample?
So we don't. What we see is the magnesium 26 that the aluminum 26 turned into. So when the grain formed, it had aluminum 26. But over the next few million years, every atom of aluminum 26 turned into a magnesium 26 atom. But because it's trapped in this grain, that ratio is fossilized in. So you don't lose it. So we still, even though it's been billions of years since those aluminum 26 atoms were aluminum, we can still detect that they used to be there.
Oh, you detected in that. How?
Detected because we can measure the magnesium that it's turned into.
Oh, okay.
Because the atom hasn't gone away, it's just turned into a different element, and we can detect that element.
Okay, thank you.
Sure. This is the same way that we measure the age of rocks on the Earth, by looking at how much uranium has converted into lead, for example.
Star evolution is so much more complicated than I thought it was before I came in here. Given that, what kind of stars died in our region to create the dust cloud that our solar system formed? I don't know if you said it or not, or maybe I missed it.
All kinds of stars. The question is when. So we think that the dust and gas that formed the cloud that formed the solar system was made from many generations of stars that had just died over time. There's another question, is whether any stars died right before the formation of the solar system. And it's quite possible that the molecular cloud from which the Earth formed also formed some massive stars that went off as supernova. And in fact, one popular way to explain why the solar system formed is that a supernova went off, and the shockwave from that supernova triggered the collapse of the gas to form the sun. And a lot of work in meteorites is trying to find clues to answer that question, to answer your question. We don't know, But it's something we would very much like to know, is what stars might have died around the time the solar system formed, what effect they had on how the solar system formed, and this kind of thing. So it's an excellent question, and I can't answer it. Huh?
In order to create life, you had to have certain elements
Right,
created. So does it make it even more rare, do you think, in
No,
context?
because the galaxy had evolved so much by the time the Earth formed, the sun formed, that there was a lot of carbon and nitrogen and oxygen and phosphorus everywhere because there had been multiple generations of stars. This might be true for the very earliest generations of stars in the galaxy, because the very first stars in the galaxy only had hydrogen and helium, and it took a while to build up to other elements. So this is a very interesting question for astrobiology. How late into galactic evolution do you have to have before you have enough elements to make a planet that could form life? And there are people addressing that question. I am not one of those people.
Thank you very much.
Sure, thank you.
One last question.
Do you know if the rocks that were brought back from the moon were ever subject to a similar investigation, similar analysis?
So not specifically looking for presolar grains. The moon was clearly the product of a completely molten, it was completely molten at one point, and the crust that we see was based on the freezing in of this molten planet and subsequent volcanism. So again, like the other question I answered, there's no hope for presolar grains to have survived. But people do look for the possibility of meteoritic material in the lunar samples that could in principle do it, but no one's found a preserved meteorite well enough preserved that we'd expect it. But there's continued interest in the lunar samples. In fact, there's renewed interest in the lunar samples, and I don't know if you saw the announcement, NASA just announced they are opening up some of the samples from the Apollo mission that have been sealed since 1971, and they're opening up for new analysis, new samples, and so there's all of a sudden a whole lot of people that are about to pounce on. They've developed, they've picked several groups, and they're going to let them work on these samples, and maybe we will see something like that. The moon is of great interest right now to NASA, and so it's an excellent question, and maybe we'll know in a few years. So.
All righty, let me remind you, tickets 10 a.m. tomorrow.
Thank you.